Hi, this is Eric Charles, and today I'm going to talk to you about Jupyter real-time collaboration. This is about Google Docs for Jupyter notebooks. So we want to offer to the user a similar experience as Google Docs. When you type something, another colleague or someone else should be able to see what you do in real time. I'm going to use quite often the RTC acronym, which stands for Real-Time Collaboration. And I'm going to first review the RTC landscape with the different algorithms, the specific Jupyter requirement we want to address. Then I'm going to review the existing implementation we have in the Jupyter RTC repository, how it is organized, with the specification we build on top, the architecture and the integration into Jupyter Lab. Then I'm going to follow up with the work in progress we have around Graphql, how we want to relayer on top of existing libraries, and the work we want to address to be performant. Before jumping into the content, let me introduce myself a bit more. So I am Eric Charles. I am the founder of DataLayer and committer for Jupyter Lab, Jupyter Server, and Jupyter RTC project. I also partner with Quantsite for different open source Jupyter projects. Happy to be here with you today to review, first of all, the landscape we have around RTC, which is quite broad. I mean, I introduced you with Google Docs. This is a tool I have used to build that slide. But maybe you know also Microsoft LiveShare. LiveShare is an extension you install into Visual Studio Code, and it allows you to collaborate with someone remote. When you write some code, some Python files or whatever, you can share your content in live with someone. Those are closed solutions. You also have open source solutions, and if you go back to 2009, maybe you have seen Google Wave. This is like the first concretization of Google moving to collaboration with a mail which is a bit more like a chat and so on. That open source project has been moved to Apache, and it is not now retired, so it's no more maintained anymore. But it was something very, very strong, which has led Google to maybe something like Google Drive. You can also maybe know HackMD. HackMD is a solution where you write a markdown file and you share that file with someone. This is available in a GitHub repository. You can clone that repository and have your own HackMD server. If you want to install an editor in your application, you have a lot of options. You have something like Remira, which is a collaborative editor, but a lot of other options are available. And if you don't want to build your own application and still today you want to use Jupyter notebooks in collaborative way, there is CoCalc, which is there since some time. It does not use the Jupyter RTC project, but it's an early adopter of that collaboration feature. Let's move on to the algorithms. So there is a lot to tell. I will not have enough time to cover even in surface what I should maybe cover. So I will invite you to go to the algorithm page of our website, which is Jupyter RTC, readthedocs.io. And there you will see that we have defined 3 categories of algorithms. The first category is OT, operational transformation. It is there since a long time, maybe 20 years. It is the one which has been used by Google Wave 10 years ago. and which still powers a Google Drive. You have some open source implementation using TinyMC, an editor, in ShareDB, a distributed database, and the characteristic of OT is that it needs a central server. We have a second family of algorithm, which is called CRDT. It is a conflict-free replicated data type. So it means that you have generic distributed data types like lists and so on. And in that case, with CRDT, you do not need a central server. So it's more like peer-to-peer. You have a lot of libraries available. Lumino is the one we use, Jupyter RTC. It's part of Jupyter Lab. You have YJS, you have AutoMerge, and so on. And finally, we have a third category of algorithm, which is a diffs algorithm. So it relies on a classical diff between documents. So you can see the diff, and it sends that diff to a server, which does a match-patch process. It is the one which is used by CoCalc. A few words about the characteristic of those algorithms. So they need to be convergent. So the convergence of the output must be ensured. If someone if a user types something and another user type another change, at the end of the day, all the user must have the same output. So the different inputs must converge to the same output for every user. This is what is called convergence. Still, this does not ensure that the output is the one which is intended. So maybe the intent of the user is not respected, it's converged, but it does not converge to the correct output. So we need a second characteristic, which is intention preservation. And still, when you review those algorithms, you may see that there are some edge cases where maybe the user type the same thing at a different place, or the network is not up every time. So maybe the algorithm is not strong enough, is not robust to those edge cases, and still they fail. This is why maybe some other initiatives come with a mix of those ideas, a mix of those algorithms, and maybe something like Microsoft Read, which has been released a few weeks or months ago, is there. It's like a mix between OT and CRDT. A bit more details about OT, for example. So once again, please go to the website Jupyter RTC, read the docs, algorithm, the OT section. We have plenty of links, and one of those links is the Wikipedia page, where you have like a scenario there where two users have the ABC sentence or ABC string, and the first user wants to insert a X at the beginning of that string, so at position 0. The second user wants to delete a character at position 2, so he wants to delete C. And those messages go to the server, they flow after to the end user, and the OT algorithm implementation needs to have that conversion and user intent. OT is more like a family of algorithm. While you have many different implementation, historically the first one was not robust, and those algorithms have been enhanced and much better in time. And to assess how the algorithm good is, you have those characteristics, which is convergent properties with CP1, TP1, CP2, TP2. You have also, if you look at how the algorithm manages the timestamp, because every user has to communicate the time when the change has been done, different methods exist. One aspect which is not trivial is how multiple servers can play into the picture, because the idea with OT is that all the transformations of the user are sent to a single server, which ensure that the parameter of the operation are transformed or adjusted based on the previous transformation, and then the result is sent to all the users to maintain the document consistency. And with multiple users, that's not that easy. So, if you want to play more, I invite you to go to that website, which is operationaltransformation.github.io. There is source code available in GitHub also. It's a React-based application, but the nice thing is that you can type a sentence, a string, and you can play like sending those messages across the network from client to server. You can, clicking on the arrows, the black arrow, the gray arrow, you can play and see all the messages will impact the server and will impact the end user. That's a very nice tool to play and to better understand what OT is. Let's move on now to CRDT. So CRDT is more like a distributed data structure. You may have counters, you may have lists, sets, sequence, maps, and so on. The idea there is that the message flowing from clients to all other clients, so the processing of that message must be commutative, associative, and idempotent. So commutative allows you, and associative allows you to play with time. So if there is some, let's say some network breakage and so on, whatever the order the message I receive is fine. And idempotent, if you receive multiple times the same message, the result will not be affected. You have also to deal with CRDT with timestamps, because when you delete a message, actually this is not deleted in the history, it's just marked as timestamp, and probably if you want to ensure more performance CRDT, you need to garbage collect those timestamps. You have two main modes, the state-based and the operation-based. Operation just sends the changes, and so it's maybe more performance in terms of network, but needs more logic on the client to merge those changes. And it is not only for real-time collaboration, so document editing. It's also used in well-known distributed databases like Redis, React, or Cassandra. It is also used for content distribution. The idea there is that you have a revision log with a list of changes. When you want to make a change, you append to that revision log your change, and the end user must replay the complete log history to get the result. So once again, I invite you to go to websites, read a lot about that. There are some nice blog posts shown here in this slide, where it takes you step by step with user 1, user 2 typing something, and all the conflict resolution is ensured. There are different methods to resolve that conflict. Here, the blog post I linked to use is the ID of the user, just like a way to add these changes before or after if there is some conflict. Nice visualization again, very cool to understand what's going on. Text-crd-compare.search.sh, it shows you how the data structure evolves when you type something in the editor for different libraries. And on the right hand side of this slide, I show also a Lumino example. So Lumino is a library we have developed inside Jupyter Lab. And when you type O, for example, you see inserted text O. This is a kind of message you see flowing the network. Cool. Now, time to move to the Jupyter specific requirements. So you all know what Jupyter Notebook is. It's a list of cells with output areas. And you may have many notebooks open in Jupyter, specifically Jupyter Lab, because this is our first target, Jupyter Lab. So many notebooks, many cells in a notebook, output area per cell, and all that model, the data models must flow across different clients. We need to ensure, for example, that when a cell is moved up or down, or when a cell is inserted, that all users see that action in their notebook. We must also ensure that when you run some code, that the output is updated in the other notebook's user. And this drives to interesting questions, because what if a user runs a code which overrides my variable? So if I have a variable x and someone types x equals something, my variable will be erased. So we need, in a way, to introduce or to manage shared kernels. That work for Jupyter Lab has begun last year in 2019, and it has been done by some core Jupyter Lab contributor, and it has resulted in what we call the Lumino Datastore. Lumino is a widget toolkit which backs the Jupyter Lab solution. It's a separated repository, and in that separated repository there is a new package introduced which is called Lumino Datastore, which manages that model and all the message are received, sent, propagated, and so on. That work is, let's say, completed with a POC, a proof of concept, end of 2019. And at that time, there are a few issues or questions that has been raised and quite difficult to move forward. And this is why we have decided, as a JupyterLab community has decided to move that initiative from Jupyter Lab to make it a dedicated Jupyter RTC project, not only for Jupyter Lab, but for any Jupyter frontend, for any Jupyter component application which needs real-time collaboration. So if you clone today the Jupyter Lab /RTC repository, you will get that a few components. You can read more on the reader docs. We have bi-weekly Zoom calls to connect with users, to discuss together what we want to do. And also we are funded by CZI grant, which is very good, because at least we have quite some manpower to deliver and to let this project evolve. We like to be we like specifications, we like having a good model on the server side, and if you want to read more on that data model, you can go once again to the website. This is an extract of that website. You can see there that we want to move from the client specs to the server. And we want to have all the notions that Jupyter has today, which is execution, code, kernels, kernel status, and so on. Good, now you have cloned the repository. What you see is a set of packages. We have what we say with the core packages, and you can see there the node, the supernode, the relay, the Jupyter. Jupyter is the one with the data model, and the relay supernode is more like the server aspect, which hosts the receive and the send of the messages. And the node is more a client which goes with React.js to his software application development. We have some tools, a debugger, a dummy store, which is like an in-memory server. And we have also example to showcase what we do, because we want the user wants to see something. It's not only having a server or having some libraries, but he wants to know how to use them. And we have the Lumino first example. So this is the one at the right top of this slide. And this is, plain Lumino. It doesn't use the other core library, but it's just something we want to show, just to have a basic knowledge and understanding of what Lumino has to offer today. We have then two other examples which does use the core packages. So the first one is a to-do application. While we all know what to-do app are, you type a to-do list, today I have to do something, and that to-do action is also shown to the other user, and you can delete also when your action is done. And talking about more specific Jupyter, we have one Jupyter example which allows you to see the data model with the debugger. So on the right hand side of the slide at the bottom, you can see there the debugger where you can see the different tables on the server. We have also updated the Jupyter Lab integration. So today you can use, with one of the latest master, Jupyter Lab, you can use RTC. This works fine. You can move cell up, down. You can select some text, and the selection will also be shown in the other notebook. So here on the picture you have one browser and a second browser, Firefox and Chrome, and they all pass the information without any issue. It works fine. We have an updated version of the work which has been done in 2019, but we need to let this work evolve to use the core packages we develop. This one is about Graphql. So one way to move the data model from the client to the server is to use Graphql, which offers nice interaction between a client and a server, and which allows you to persist that data model on the server in many different implementations. And what we want to do is move from that GraphQL interaction and build collaborative features on top of that GraphQL channel. Also that collaborative way, we have that Lumino library, the Jupyter La Premium, but this is not the only one we want to address. We also want to leverage other existing real-time libraries like YJS, like Automage, like Freed, and so on. We are looking to build like a layer which allows the application via our packages to use existing RTC libraries. And to serve a lot of users, we need to be performant. I mean, if you remember, you've seen the payload of the message just for one character, which is not tiny, and so we need to make sure that the different operations we serve are performance, that the payload of the message are not too heavy. And for that, we are looking at existing benchmark, and we add to add our implementation to those benchmark. We also need a scalable platform. If we have a few users, a simple server will be no issue at all. A simple Python or Node process will not be an issue. But if you really want to scale to a lot of users, you need to deploy your service on something like Kubernetes, which is a distributed platform management, and also maybe you want to transfer messages in a more async way across those distributed services, and something like Kafka, which is a distributed message queuing system, is also something we are looking for. Yeah, so thank you for being here with me. I hope you had good overview. Is just an overview of what we do, an overview of the algorithms we use. And if you want to jump into the code with us, I invite you to try the examples. This is the very first step you could do. So just go to Jupyter Lab RTC on GitHub and go from there to the documentation on the reader docs and follow the very simple steps to run those examples. We are also looking for user stories because, well, we need to hear from you. We need to know what you need. So come and join, open an issue, come to the Zoom bi-weekly meeting. And if you are more looking for helping us on documentation or design, we need you. We need better docs, we need a logo, and so on. And if you just want to use the library, that's fine also, but be aware that this is still a work in progress, so the API is quite unstable, I would say. So once again, thank you to all. Thank you to CZI for the grant, and have a good time. Thank you.